Welcome to my Physics 2 Lab 2. This lab involves observing the interactions between prepared pieces of charged tape. Its purpose is to do a charge tape interaction experiment to determine approximately how much excess charge is on one piece of charge-clear tape. This lab utilizes Coulomb's law, which shows how charge models the force between two point charges, and it uses the law of gravity to explain the attractive force between two masses. Here's a preview. The main result of this lab is a setup of two pieces of charged tape, called U-tapes, interacting with another identical U-tape from below and attempting to create an upward electric force that counteracts the downward gravitational force on the upper U-tape due to Earth. The resulting data is used to computationally calculate the amount of excess charge on one of the pieces of tape, fulfilling the purpose of the lab. For the entirety of this lab, this setup, one tape fixed above the other, is modeled with GlowScript as two lines of evenly distributed charge exerting electric fields on each other. The system is the top U-tape, and the surroundings are the bottom U-tape and the Earth. And then the forces on the system are gravity, and we use the law of gravity, and then the electrostatic force, where we use Coulomb's law in order to model the force between every single pair of charges. We have to make assumptions, obviously, to successfully do this lab. It is assumed that each piece of tape is a one-dimensional distribution of charge, which allows the total force between the tapes to be modeled by a Riemann sum of the forces between every pair of individual charges in the lower and the upper line. It's also assumed that each U-tape has about the same amount of charge evenly distributed along the length of the tape, which allows dQL and dQu to become the same value, and then they become dq squared in the calculations. Here's the experiment. So the length of the tape was 19 centimeters and its mass was 0.00019 kg. The distance between the two tapes was 1.1 centimeters. And then the magnitude of the gravitational force on the floating piece of tape was 0.00186 newtons towards the Earth. And then the magnitude of the electrostatic force was the same thing away from the Earth. And then the charge on one piece of tape, modeled as a line of charge, was estimated to be approximately 1.56 times 10 to the negative 8 coulombs. And here's the code. So for every tiny charge in the upper tape, the model calculates the force on that tiny charge due to every tiny charge in the lower tape. And then it sums all this to get the total electric force on the upper tape due to the lower tape. And we can run it. And you see that the net gravity and the net electric force are equal and opposite. Yeah, so the model predicts it and it looks good. Yeah, the charge on one piece of tape was approximately 1.56 e to the negative 8 according to the forces produced by the computational model given the tape of same length and separation distance as the experiment's observation. And we use trial and error to find this. And then the assumption on the given list made for this line charge model was that the code assumed that each U-tape had about the same amount of charge evenly distributed along the length of tape. Then we hand calculated the value based on experimental observation for the total charge on one piece of tape was much smaller than the value according to the forces produced by the computational model. The hand calculation treats the tape as a point charge, meaning that every charge within the tape creates a much stronger field at the location of the other tape in the line model. Using the computational line model, the charges in one tape are individually more distant from the location of the other tape, weakening infinitesimal fields and therefore requiring a larger total charge to maintain vertical equilibrium for the system. Here's the discussion. It is possible that handling the charge tape with precise machinery could have made it more accurate. Obviously, there's some error with hand calculations. And then this experiment shows that electrostatic interactions between lines of charge, or what are assumed to act like lines of charge, can have significant effects on their motion. Yeah, if the tapes were modeled as point charges, the calculated total charge would be significantly smaller. 1.56 times 10 to the negative 8 coulombs for line model, and 5 times 10 to the negative 9 coulombs for the point model, which would cause the electric force calculated by the computational model to also be much smaller and not even cancel gravity. And then these estimates differ because while their calculated forces are the same, the distance between opposing charges significantly decreases when the tapes are point charges. Basically, the charges in the point model produce a generally stronger field than when the charges are spread out, which is why the total charge to create the same forces is smaller in the point model than the line model. Here. And then here are my conclusions. Objects which are polarized by the electric fields created by charged objects tend to be attracted toward the charged objects. Charged ordinary objects created in the same manner repel each other, and they gain back so much net charge that the magnitudes of the forces on each other from the electric fields they create can match and even undo the magnitudes of the gravitational fields between them and Earth. And then treating the same totally charged object as a point or distribution of charges over a line